Okay, so let's get back here. Why is this modify so many times? Apple and their stupid iCloud? All right. So we a few minutes ago we were talking about arrays and kind of the strengths and weaknesses of arrays. And again, I'll reiterate that I don't want you, as we start talking about this new stuff, don't view arrays as being bad. Okay, arrays are not bad. We use arrays all the time. We still use arrays all the time. But we want to look at some alternate solutions. And one of the things that we might look at for linked lists, so let's just kind of talk about some features. So we're going to say linked list strengths, very memory efficient. Weakness, slow. Again, relatively speaking. Computers are really fast, okay? But weakness is these guys are relatively slow because we cannot, because of the effort we have to take to make them memory efficient, which we'll talk about, we then have the downside of we can't just compute our way to a place in memory where a certain element lives. We have to traverse the list from beginning towards the end until we get there. Make sense? All right, so kind of I guess kind of a thing. It's a trade-off, if you will. So when would we use linked lists? So used when we need to store an arbitrary amount of data. All right, so when we don't know how many things we're going to need to store, maybe it starts off as 5, then goes to 6, then goes to 12, then goes to 13, whatever. When it's an elastic type situation, when the amount of data we need to store can change, a linked list typically makes a lot more sense than an array, unless performance trumps efficiency, memory efficiency. Okay, so anytime you need something to be really, 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 really fast and you don't care so much about memory efficiency, arrays are probably going to win. Okay, and now keep in mind though the type of world we live in today and when these things came from. You can find some really old dusty books that talk about linked lists data structures from years and years and years ago, from the 70s and the 80s, that talk about linked lists. We lived in a different world then. Okay, so the idea is that memory efficiency was a big deal then, right? Okay, memory was expensive. I used the example in the 535 class. Usually I talk about the 8 megabytes of RAM I put in my computer in 1996. Okay, an 8 megabyte chip cost me $1,000. Okay, and it comes out to about $125 per megabyte. Okay, $125 per megabyte. Today, RAM prices is about a penny per megabyte. Okay, so punchline is that some of these things that we used to care about, we care about less today. All right, so this idea of memory efficiency only maybe comes into play in the highest echelons. Okay, if you're doing some real scientific type thing where whatever you're doing, the simulation you're writing is maybe just using ridiculous amounts of RAM. Okay, where creating an array that's 40 gigabytes big in order to hold something becomes a problem. Okay, we don't have that kind of RAM today yet. The most I've seen in a consumer machine is like 32 gigs or something like that, right? But punchline still is that would be a very extreme situation. Okay, so realistically today, we're probably really not going to care about the memory efficiency thing very much. All right, because memory isn't the enemy anymore. Memory's cheap. Okay, we can always add more memory if we had to. All right, so even though linked lists are memory efficient and arrays are memory inefficient, that becomes something that's not that important through today's lens. Okay, but now we still get down to this idea of holding arbitrary amounts of information. So when we're choosing whether to use an array or using a linked list, maybe the decision is less about speed, since our computers are really fast as well. So just as linked lists are memory efficient and slow, how slow they are really isn't that important because computers are really fast. So just as memory isn't a problem anymore, the speed slowness of linked lists really isn't a problem either. Okay? So really what it comes down to is when we're trying to decide what's the right tool for the job. If we go into Home Depot and we're trying to buy a tool to do something, in this case we're storing some information. If we know the exact amount of stuff we need to store, we're going to buy an array. If we know we're going to need to store a potentially growing number of things, but we have no idea how big it's going to get, we use a linked list. All right? That's probably the simplest way for us to look at it through today's lens. We want to appreciate that memory used to be a big deal. Okay? That we used to maybe make decisions towards linked lists because we didn't run out of system memory. Okay? But that's not an issue now. All right? So we want to think about linked lists as being they're like elastic arrays. They're arrays that we can just keep adding things onto, and we don't have to destroy the original. Okay? The way arrays work, and we think about from like a house analogy, you just buy a plot of land, you build a beautiful house, you decide you want a deck. You decide you want to add a deck into the backyard. You're going to burn down that house. Build a brand new one that's a duplicate of the original one, but with a little bit extra space for a deck. That's how arrays work. That would never make sense in real life. Okay? The array version is when we know exactly what that house's footprint's going to be. We buy the exact plot of land to hold exactly what we need. That's an array. All right. The linked list version in real life would be something like, we're going to start off with a house this big, but we're going to buy a plot of land that's this big so that we can expand as we see fit. Something like that. Okay. But this idea of memory is kind of out the window now. So for our perspective, rule of thumb is going to be linked lists make sense if we don't know how much we're going to store. Arrays make sense if we do. Okay? So let's talk about linked lists then. Let me actually steal some of this stuff. Okay, so this is our 5-bucket array that we had before. I'm going to show you this in a linked list style. Okay, so what we're going to have here is I'm going to kind of spread these out. All right, so now the thing that's going to change here, though, is those memory locations. I'm actually just going to get rid of these because the memory locations are no longer important. We know they live somewhere in memory, okay? But when we have a linked list, here's bucket 0. Bucket 0 is going to be linked to bucket 1. Somehow, those guys are connected to each other. We cannot mathematically say, oh, well, bucket 1 is one memory address over, size of int memory address over from bucket 0. That's no longer the case with a linked list. This guy might be on the other side of RAM. Okay, he might be 300 megabytes over. We have no idea where he lives. So we have to have some way, a pointer that's in this node that allows us to traverse to this guy. All right? We can't just jump to bucket 1. We have to start at bucket 0, then ride the roller coaster from bucket 0 to bucket 1. Okay? Similarly, bucket 2 is traversable once we're at bucket 1. Bucket 3 is traversable once we're at bucket 2. Bucket 4 is traversable once we're at bucket 3. All right, so to get to bucket 4 of our, I call them buckets, to get to the 4th element in our linked list, we would start at the beginning, walk to number 2, or walk to number 1, walk to number 2, walk to number 3, finally arrive at number 4. Okay? So we have to walk through memory to get there. All right, so you can't just go directly to bucket 4. Okay, so that's where it's memory efficient. We don't need this plot of land all one size to fit all this stuff in. We can now just have enough memory in some place in memory to hold this guy. Then enough memory someplace else in memory to hold this guy. And enough memory someplace else in memory to hold this guy. So on and so forth. And then we link them all together so that we have some way of getting to them. All right, that's why it's slow. We can't just compute and jump to a place. We have to traverse it. Okay, but it's memory efficient. Make sense? But the nice thing here, so that's kind of our visual picture of what a linked list is compared to an array. The nice thing is, though, if we want to add a 5th bucket to my array, I have to build a brand new array that's 1 bucket larger, copy everything over from the original, put my new element in, and then overwrite the pointer of the original with the new one. Okay? I have to basically build a brand new house with a little bit more room. If I want to add 1 more bucket to a linked list, I just add the bucket and then connect it off the end of the list. I didn't have to destroy anything. I just tacked it on. Make sense? That's the visual advantage of a linked list. When we need to hold arbitrary amounts of data. Okay, they can grow and shrink as we see fit. Similarly, up here, if I want this array to be 1 smaller, I could choose just not to store anything in that bucket. But if I want to literally cut that bucket off, I have to create a new array that's 1 bucket smaller, copy everything over except the thing I'm getting rid of, then overwrite the original with the new one, the memory address. We're here, if I want to get rid of this dude, gone. Just disconnect the pointer. Let Java's garbage collection clean up the mess. Right? No harm, no foul. So linked lists are really convenient from that perspective. All right. So do we have a general idea on kind of visually what a linked list is? All right. So now let's think about writing these guys. So for your homework assignment, just so you can kind of think ahead, I already have it up here. Let's just look at it here real quick. It's actually an incredibly interesting and a pretty difficult assignment, though. As we're going through this stuff, I want you to be able to think about the context of the assignment as we're going through it. All right, so you have 2 different assignments. There's a report assignment that you have to write. It's a 2 to 3 page paper. It's double-spaced, that stuff. I care a lot more about that you guys improve your writing. Okay, so that's why I'm encouraging you to go to the writing center and that kind of stuff, because that is going to be your challenge if you end up staying here and working in the States. Is your written and oral communication, because English isn't your first language, and that is the challenge. So, you know, I realize this is your least favorite. I think actually Blade had a quote in the last class that he wants twice as many programs and no papers, right?
Yeah.
You don't like the papers. Okay? Well, nobody likes papers. Okay, but realistically, you guys probably need it more than a lot of other folks do, because you need that communication in order to set you apart when you're applying for jobs, at least here in the States, right? You go back home, you can already talk with the people back home, but if you're staying here, you'll thank me later. You're not going to like writing them. I know you won't, all right? But try to do a good job on the papers and work on your communication skills, because I've placed a lot of students that come out of our grad program in positions, and people are impressed with the folks that have really good English communication skills, because they go in perceiving that you won't. All right? When you apply for a job here in the States and you have some funny name that the person can't pronounce, okay, they're going to automatically assume that, oh, this person's not going to be able to speak English. We're just going through the motions of trying to hire them, or, you know, interviewing them so we don't get in trouble by some affirmative action thing or something like that. Okay? If you can impress them with your English speaking and writing skills, you're actually going to get the job ahead of a lot of other people, because your technical skills are typically better than the American technical skills are. We already talked about that. The evidence is right here. You know, here's a graduate course, and there isn't one American in this class besides me.
Yeah.
Huh?
I'm a resident here.
Well, but you get what I'm saying. You know, somebody who was born here, right? You know, I am the minority in this room, okay? And that's not just Concordia, that's across the board. So you guys are already coming in with a technical advantage to other Americans in terms of skill set. Now what you need to do is you need to catch up with your communication. Okay, so the part of the class you like the least is the part of the class you probably need the most work in. Make sense?
Yes.
All right, so try to view it through that lens when you go through that stuff, because that's the punchline. Okay? I tell my students all the time that I don't, America outsources so much stuff to like India, and now China is becoming a big place for outsourcing as well. And the Americans are complaining, oh, we're losing jobs. Well, if you're a business owner and you can pay half the price for twice the competence, why wouldn't you? Right? I don't need these people to talk to me or write papers. I need them to write code at half the price. So, you know, you already have the advantage here with your technical skills and your motivation to improve. So work on the writing skills, and you guys are going to be way ahead of the curve for getting jobs here. Okay, so the paper you're going to write for next class is discussing the advantages and disadvantages of linked lists versus arrays. So kind of the things we just talked about. We talk about when would each of these be the right tool for the job. So continue to explore this idea of what we've spent kind of the last 15 or 20 minutes talking about. This idea that linked lists lend themselves to certain things, arrays lend themselves to other things. You could talk about kind of the history of it from a memory perspective, but practice the writing. So hopefully you're comfortable with the topic now since we've talked about it. Practice your writing in that context.
I think this topic is easier than last class.
Well, I think the topics will get harder.
No, I mean
and more arbitrary.
The paper topic is easier.
Yeah, but some of my other paper topics are worse.
Okay.
Yeah, so don't get your hopes up, is what I'm saying. Because I wrote these paper topics a long time ago, so I have no idea what they are.
Okay, so it's different.
Yeah, it really depends on what my mood was back then.
Okay.
Yeah, I just pulled this one out of the online course and said, this is what your assignment is. I had to check it too. Make sure I cover the right crap.
Hope you can always choose the easier topic first.
Yeah, but that's not any fun. Remember that Solaris paper? On Sun Solaris in 535?
Yeah, I remember.
Isn't that a great paper?
That was good. We didn't get anything from
I
it.
didn't like it.
Yeah, when I first had that assignment, the issue was that Sun Microsystems was still around, and there was a whole lot of documentation on Solaris.
Oh, I remember. It's so terrible.
And then once Oracle took them over, they got rid of all the documentation.
Yeah, it is true. It's really hard to find the
Yeah.
documentation.
Yeah. So I'm gonna be changing that paper, but
Actually, I even don't know if the reference I find is correct.
yeah, it could just be made up.
Yeah.
Yeah, I mean it's almost a wasted paper because when I grade that, I don't grade it so much on content. I grade it on writing.
All right.
Because it is difficult to come up with enough sources for that. This one you won't have problems.
Indeed.
There's
have a lot.
going to be plenty of crap on linked lists and arrays and that stuff. Okay, so now here's the other side. Our programming assignment for next class, and we're going to start writing part of it here today. We're going to start writing our linked list part. So you're going to implement your own linked lists, which, like I said, we're going to start doing here. All right? Like I said already, you can't use any third-party implementations of linked lists. You got to write your own. Okay? So only things that we've shown here in class. So any abilities you need your linked list to have, you're going to write. All right? I'm going to get you started today. So then implement a class called huge integer, okay, that represents arbitrary sized positive integers and supports addition only. All right, so when we talk about like normal ints, a normal integer in Java can only hold values up to 2 billion, negative 2 billion to positive 2 billion. Well, that's not arbitrary in size. What if I want you to hold a number that has 4,000 digits in it? Okay. Long only holds up to like 9.2 quintillion or something like that. Not 4,000 places. Okay, so the point is that we get but you don't know about big integers. You're writing your own big integer. It's called huge integer. Okay, I had to name it huge integer because big integer is already taken. All right. So punchline is if you want to represent arbitrary length numbers. Okay, a number that has any number of digits in it. Okay, we probably need something like a linked list to do that. All right, so you're going to create an object called huge integer that's going to be based on a linked list. So we're going to use the linked list data structure to store the contents of a huge integer. All right, then we're going to have these huge integers capable of adding themselves to other huge integers, producing a huge integer result. Okay, so if I take one 4,000 digit number and I add to it a 3,864 digit number, that's going to produce another gigantic number that will be a huge integer. All right, so you're going to be writing this huge integer class, and it's going to support just addition. Okay, just addition. So taking one huge integer, which is a linked list representation of a number, and another huge integer, which is a linked list representation of a number, add those guys together, producing another huge integer. Make sense? All right, so in order to pull that off, we need to have a place to store the digits of our huge integer. Okay, so we're going to start building that tool today, then you guys can finish building it as part of your homework. But we'll get a good chunk of it done. Okay, so let's go back here. And let's talk about the starting point for a linked list data structure. All linked lists have a head. This guy points to the beginning of the list. Okay? So this one variable called head always tells us where the front of the list is. So if we're coming to our picture here, I have a variable somewhere here called head, and head points to the very first element of the list. Okay? That's what head is. Points to the very first element of the list. Because like I said, in order to get to bucket 3, we have to start at bucket 0, traverse to 1, traverse to 2, then get to 3. I need to have some variable that tells me where to start. Okay? Which house do I go to first so that I can find the second house? So I can find the third house. Make sense? So that's what head is. Now, each of these guys is a node. Okay, we're going to call them nodes. So a linked list is a collection of nodes that are connected to each other. Okay? So generically, a linked list has a head. Then we have a class called node. What's a node? A node has a payload. This is the value stored. We have a next node. This is a pointer to the next node in the list. Make sense? All right. So a node, this guy right here, he holds a value. So maybe the value here is 4. That's his payload. And he has a next node that is a pointer to the next guy in the list. Make sense? So these are our players. So in a linked list, we have a bunch of nodes hooked together through node pointers. All right. So let's go ahead and build these simple data structures. So right here, let's start with node. Isn't this a data structure? This is a data structure capable of holding a piece of information as well as the pathway to another data structure. It's no different than when we talked about fractions holding a numerator and a denominator. This guy's a node who holds a payload and a next node. It's a data structure just like anything else. And we're going to use this little data structure to build a bigger data structure, kind of like Legos. Okay, this is one of the small yellow Legos, and we're going to use it to build a bigger Lego. All right, so let's go into Eclipse over here. And I'm going to go ahead and I'm going to create this class for our node. All right, so there's our node class. And we've said that nodes are going to hold 2 pieces of information. They're going to hold a payload, and we're going to create a linked list of integers, seeing as our homework seems to like it's going to require us to hold a bunch of integers, right? So let's make something that's compatible with that. All right, so our payload in any individual element of our linked list, any one of these guys, the payload is always going to be an int. Okay, in our linked list here. So I'm going to create a private int payload. That's one of our attributes for our node. And then we're going to have a next node. That is a pointer to another node in the linked list. Okay, so this is going to be a private node called next node. So first guy is of type integer, the second guy is of type node. Okay? Now we need to have a constructor for our node. When we build a node, we're going to take in a payload as a parameter. And we'll say this dot payload is equal to payload. And then we're going to go ahead and we're going to say this dot next node is equal to null. By default, when a node is born, it's not connected to another node. We will connect it to another node, but when it first comes into existence, it's not. Make sense? All right. So purpose of a constructor. So hopefully this is going to be review for some of you, but some of you maybe haven't programmed in a while, so this is all fuzzy stuff. Purpose of a constructor is to initialize the base values for an object. So I'm giving payload and next node a value. The value for the payload is coming in through the constructor. Next node, we're just defaulting to null. Okay? So that's what a node is right now. That's our simplified version of a node this very second. All right, now let's go ahead and let's create our linked list class. So we'll create a new class called linked list. And we said that a linked list is going to have a head, private node head. And when we build a linked list, it's going to require no parameters, and we'll just say this dot head is equal to null. All right, so an empty linked list is literally a variable called head that points nowhere. Okay, because we have nothing in the list. But it's a starting point to start putting stuff into the list. All right, so now, so far, everything we've advertised here, sorry about that. Everything we've advertised in both node and linked list are all attributes or fields. These are pieces of information that we're remembering, not necessarily things that they can do. All right? So now that we have this basic structure for a linked list, just like my shoe bench at home, now I need to decide how am I going to use that shoe bench with my shoes. All right? Similarly, how do I get stuff into my linked list? So we're going to start off, we're going to add an ability for, that's just weird. Why does it keep doing that? So we're going to start off by creating a function called add front. This adds a new node to the front of the list. Okay? That's what add front will do. So we're going to have a method called add front that will build a brand new node and add it to the front of the list. So if we look at this picture here, let's go ahead and just give values for all these guys just to say we did. All right, and let's say I bring a brand new node into existence. So here's my new node. You know what, really, it's probably going to behoove us just not think about these in terms of indexes. I think we've covered enough to kind of understand where those guys kind of live. All right, so now I have a brand new value, 14. And I want to add this guy to the front of my list. So ultimately, I want him to come before the number 2 in this case. So how do I do that? Well, I'm ultimately going to need head to point to this guy. But if I do that right off the bat, what did I just do? I lost the rest of my list. Okay? I can't set head to something else yet. So what I actually need to do is I want this guy's next node to point to the same place that head points to. So I create my brand new node, and then I make his next node point to the same place head points to. Then I can make head point to this guy. Make sense? All right, so first thing, create the new node. Second thing, set that new node's next node equal to the same thing that head points to. Then I can update head because we now have a new front of the list. Make sense? All right, so go into our code here. So here's our linked list. We're going to go ahead and we're going to create a public void add front. And let's say this guy takes in, let's call it a value. He takes in a value. All right. Now, in order to add something to the front, what we need to do is we need to first create a new node, right? So we're going to say node n is equal to new node, passing it value. We design node here. Node takes in a payload. And what does it do? It sets that particular node's payload equal to whatever we passed in. And then it defaults the next node to null. Okay? So what have I done right here? I've created a brand new node object that currently holds the value that I'm trying to add to the front of the list, but doesn't point anywhere. Next thing we said we have to do is we need to make this guy's next node point to the same place head points to. Okay? So, how do I set this guy's next node? Currently, I can't. Next node is a private variable, and it should be. Okay? Remember from last semester, we want all of our variables to be as private as possible. Okay? Lock them down and only loosen them when we have to. So what we're going to have to do is we're going to create a setter for this, as well as a getter. So we need to be able to set the value of next node and also get the value of next node. All right, we can write these by hand, or Eclipse also has a built-in mechanism for getters and setters. So I can just right-click out here, go to source, go to generate getters and setters. And I'm going to go ahead and I'm going to select both get next node and set next node for this guy. And then I'm also going to go ahead and get the payload. I don't need to set the payload. That gets set when we first create the node. But I do want to be able to ask for the payload from a node. What is your value? Okay? And I do want to be able to get the next node as well as set the next node. So I'll use this little wizard here to generate those getters and setters for me. So that's going to build those in for me. Now, the first thing I always do with this, for those of you who remember from last semester, I like this syntax like this. I like the curly braces to be directly under it. I'm not going to take off points if you don't do that. But punchline is I've been programming longer than you have. Trust me, this will benefit you. Okay? It's much easier to debug when you see the beginning and end of a code block right next to each other. So as your programs get larger and larger and larger, having this as a habit will become easier. All right. I know a lot of you, or at least, well, really a lot of programmers have that habit of putting the opening curly brace at the end of the first line. Do you know where that came from? Probably mentioned it in last class as well.
In the book, want to save space.
Yeah, it came from textbooks. You know, when you had programming textbooks, they needed to save a line. Printing is expensive, so they moved the curly brace up to that line. Well, people started learning to program out of these books, right? So they adopted that as their pattern. And even our compiler, our IDEs today are doing that by default. I think it's a terrible, terrible programming practice, but not uncommon. All right, so my suggestion would be always fix it to look like this, but whatever makes you happy is fine. All right, so now we've expanded our definition of node a little bit. All we've done is given ourselves some access to our fields, our private fields. Okay, so now we have access to those things. So now I can go back into linked list and I can say n.setNextNode equal to head. So I can make n's next node point to the same place head points to. Okay, and it's important that we understand this. So now we're starting to deal with pointers. We go back into our picture here. When I say head points here, this guy has a memory address. Okay, let's say this is memory address 100 for our little example here. Okay, so this guy actually has a memory address where he lives. head, when we say head points there, what we're actually saying is head holds a value, and the value head holds is equal to the memory address where this guy is. That's what we mean by saying it points there. Okay, so when we take our new node here, this guy, this is n in our example, and we set his next node to head, what we're doing is we're setting n's next node equal to memory address 100. So this guy points to memory address 100, this guy points to memory address 100, this guy is memory address 100. Make sense? Okay, so that's what we're saying. When we go to this line right here and we say n dot set next node to head, we are taking the value of head. Head is a variable. Variables hold values. The value that head holds is not a node. It's just weird. Okay, the value that head holds is not a node. It's the address where a node lives. Okay? This is the value of head. That is not a node. That's a memory address. Okay? Let's prove this real quick. I'll come out here to our driver. We're going to say node n is equal to new node, and we'll make this guy a 5, and then we'll say system.out.println n, and we see a nice little memory address. He's a memory address. All right? So if I say node head is equal to this guy, and then I print out head, I just changed the variable name, right? I print out head. This guy is a variable. That variable resolves to its value. The value of that variable is a memory address. That happens to be the location where a node actually lives. Okay? This would be the same thing where if I wrote on a piece of paper my home address and I handed it to you, okay? And then somebody came and beat you up and took the piece of paper from you, they wouldn't have my house. They would know where they can find my house, but they wouldn't have the actual house. Make sense? So head does not hold a node. It holds the address of a node. Make sense? All right, so we need to get comfortable working with these memory address things, even though pointers don't exist in Java. All right, so in any case, we set n's next node equal to the same thing head is equal to. Then we can update head to hold the address of n. So maybe this guy, maybe n is now memory position 312. So now head would equal 312. Okay? It doesn't hold this node. It has a piece of paper that tells us where we can find that node. That's the address. So go back into our code here, linked list, create our new node with the value, set that node's next node equal to whatever head is equal to, then set head equal to that next node. Make sense? All right, just so we can see this work, what I want to do is I'm going to go ahead and I'm going to build into linked list the ability for a list to display itself. So we can kind of get a visual of what our linked list looks like. All right, so we're going to create a public void display. And this guy's going to go ahead and go through our linked list, displaying each element in our list. Okay, so what are we going to do? We're going to ask if head is equal to null, let's say empty list. Else, if head is not equal to null, then what we need to do is we need to ask head to display itself. So we're teaching linked lists to display themselves. Linked lists display themselves in terms of nodes being able to display themselves. So I'm going to go in here and we're going to say node has the ability to display itself. Public void display. All right, so a node is always going to display its own payload. first. So we'll say system.out.print, just so it looks pretty. We'll do prints instead of printlns. And we're going to say this dot payload. And we're concatenate onto that a little arrow. Like that. Okay? Now, if this dot next node is not equal to null, that means if we have a next node, if this node is linked to another node, then we'll say this dot next node dot display. Make sense? Otherwise, we'll say system.out.println. Let's just say end, something like that. Okay, so what does a node know how to do? It knows how to display its payload as well as ask its neighbor to display itself. What does its neighbor know how to do? It knows how to display its payload as well as ask his neighbor to display itself. And we keep doing this over and over and over again until what happens? Until we finally run into a situation where a dude doesn't have a neighbor. So he just says end instead of asking his neighbor to display himself. And that's the end of it. So now in our display for linked list, if we have nothing in our list, we're going to say empty list. Otherwise, we're going to say this dot head dot display. That is the first node in our list. Head points to the first node. We'll ask the first node to display itself. What will he do? He'll display his value, followed by an arrow, followed by, if he has a neighbor, he'll ask his neighbor to go ahead and display himself. Okay? So that's our display method for linked list. So what we can do here is let's just go ahead and start creating a little model here. So we're going to create a linked list. LL is equal to a new linked list. All right, and then let's do ll.display. So this should give us empty list to begin with, right? Because we have nothing in the list. So when we say ll.display, it's going to come in here. It's going to say, oh, head is equal to null. Why? Because head is null by default when we first build a linked list and don't put anything in there. So if head is equal to null, we're just going to display empty list. So that's what the output of our code will be right now, empty list. But now I'm going to add something to the front. So before I display it, I'll go ahead and say ll.addFront, and let's add a 5 to the front. Okay, now we'll display this. So this should show a 5 followed by an arrow followed by end. Okay, if I add a 7 in front of the 5, now it should be 7, 5, end. Make sense? All right, we're adding to the front of the list over and over again. So that's one ability we have. Got it? All right, so now we know how to add front. What about add end? This adds a new node to the end of the list. Well, adding to the front's easy because we know where the front is. The front is wherever head points to. Okay? Where is the end of the list? So if I'm looking at this picture, how do I know I'm at the end of the list? Yep. When we get to a dude, we get to a node whose next node is null. That's the end of the list. Make sense? All right. So let's get rid of some of these red squares just to clear this out a little bit. So I start here. If I'm saying I want to add a brand new node, so let's add a 3. So I'm going to create a new node I want to add to the end. All right, so we'll create that node. He currently has a next node that points to null. Okay, so he points nowhere right now. So that's this guy. This is n. All right. Now we need to traverse our list, starting at head until we get to the end of our list. All right. So we start at head, so we're pointing right here. Is this the end of the list? No, because his next node is not equal to null. Therefore, what do? We set our current node that we're looking at to our current node's next node. Is this the end of the list? Nope. Set our current node equal to our current node's next node. Is this the end of the list? Current node is equal to current node's next node. End of the list? No. Current node is equal to current node dot next node. This the end of the list? No. Current node is equal to current node dot get next node. Is this the end of the list? Yes, it is. So since this is the end of the list, what do? We set this guy's next node equal to n. Okay, we just hook it up. So adding it is actually easier for adding end after we've traversed to the right place. Where adding to the front is more difficult to add it because we need to make sure we don't lose the second value, the new second value of the list. All right, so we have to write our code. We have to write a couple different versions of the code here. We have to write a piece that traverses our list to the end. All right, so let's go ahead and do this. So let's go into our linked list. We're going to do a public void add end, and this guy's going to take in a value. All right, now what if we are looking at the empty list? How do I know a list is empty? Yeah, head is null. Yeah. I don't want to look at the payload because there is no payload in a null value. So if head is equal to null, that means I'm looking at the empty list, right? And if I'm looking at the empty list and I'm trying to add something to the end, isn't the front just as good as the end? So I can say this dot add front value, since we already wrote that logic, right? All right. Otherwise, if I am not looking at the empty list, I need to traverse to the end of the list. Okay, so I need to traverse to last node in list. So let's go ahead and let's build our node here real quick. So we'll say node n is equal to new node value. Then we need to traverse to the end of the list. So what we're going to do is we're going to say node cur node is equal to head. We'll start off at the front of the list. So we created a second pointer that points to the same place head points to. So I have essentially done this. Whoa. I've created another variable called Cur Node that happens to point to the exact same place head points to. I can change this guy. I don't want to change this guy because I'll break my list. Head must always point to the front of the list. Okay? So, we're going to say while Cur Node dot get next node is not equal to null. As long as there is a next node, we'll go ahead and say Cur Node is equal to Cur Node dot get next node. When we're done with that loop, Cur Node will be sitting on the last node. That is the node that does not have a next node. All right, and what do I do with that guy? I say Cur Node dot set next node to n. Here's the node I'm adding. Let's travel to the end of the list. Then go ahead and tack the new guy onto the end of the list. Make sense? So let's go back to our driver here. We add 5 to the front, we add 7 to the front. So right now we have 7, 5. Now let's go ahead and let's do ll.add end 3. Now we should have 7, 5, 3. 7, 5, 3 end. All right, so now we put the guy at the end. Make sense? Okay, so now let's go and remove from front and end. All right. So remove front, we'll write that first. So let's go ahead and give a definition in here. Where's our linked list? Remove front, removes, and usually and returns the payload of the first element in the list. Okay? Which means that there's a new first element of the list after this guy's gone. Okay? So we come back to our picture here. If I say remove front, I want to ultimately return the number 14, the payload of this front node. All right? But I also want head to point here. And I want this guy to not point anywhere. So he can be automatically garbage collected. All right, so we got to look at what the cadence is. So the very first thing we want to do is we probably want to grab the payload that we want to return. Okay, let's go ahead and grab the whole node, and then we can get the payload later. Just in case we ever decide we want to have the whole node returned rather than just the payload. So we'll go into linked list. Let's put remove front right underneath add front. Public. Right now we're going to have this return an int, the payload of it. Remove front. All right. So we're going to say if this dot head is equal to null, that means we have an empty list, nothing to remove. Actually, you know, the correct way of doing this, since this does return an int, would be this. Okay, it should actually throw an exception. So if head is equal to null, we should throw can't remove from empty list. All right, so that's what we'll do in the event that we're empty. We'll throw a new exception. So this is how Java, a modern language, handles errors like this. So it allows us to do exception handling and exception throwing. All right, so we'll throw an exception saying, hey, the list was empty. We can't remove from the empty list, and this keeps us from having to return a value, since this method expects us to return an int. Else, if I'm here, that means I do have something to return. All right, so if I'm here, I'm going to go ahead and say node, call this node to return is equal to head. So we'll have node to return point to the same place as head points to. So what did we just do there? We did this piece. We create a variable. Had them point to the same place as head. I don't remember, did I name them like that, or I say the word TO, whatever. This is node to return. Okay, so both of these guys point to the same place. Now, I can set head equal to node to return dot next node, or I could set head equal to head dot next node. Same thing. So I ultimately want to do this move right here. Okay, so we're going to say head equals to head dot get next node. That'll move head forward one thing. Okay, so that's that piece. Then we're going to say node to return dot set next node to null. We want to completely disconnect him from the list. Okay, so that'll disconnect him from the list. So now it looks like this. My new linked list is intact. Head points to the correct place, right? My node to return is sitting right here. We still have access to him, so we've preserved that so that we can move head. And we've completely disconnected this guy so that automatic garbage collection from Java can come through and clean this guy up. Get rid of him, since in a modern language like Java, unlike C and C++, we're not responsible for cleaning up our own messes. There's a garbage truck that drives around the Java memory environment looking for abandoned chunks of memory like this. That is memory that's no longer pointing anyplace. That we can't get to it. Okay? So the very last thing we're going to do, our list is in good shape. We need to return the payload of node to return, because we've promised we're going to return an int. So I'll say return node to return dot get payload. Make sense?
Okay. Can I ask you a question about garbage collector? Just as you said, if point is pointing to a noun, then it will be thrown away by Java. So for the linked list, the final node is point to a noun.
But something else points to him.
Okay.
Yep. So
If someone
even though this guy points to null, there's a way of getting to this guy. Yep. Yeah, so to kind of clarify this, every object in any programming language really has something called a pointer count. Okay? It's a counter that is the number of things that point at that guy. This guy has a pointer count of 1. This guy has a pointer count of 1. This guy has a pointer count of 1. So for each of these guys, exactly one thing points to them. In this picture, this guy has a pointer count of 2. Okay, so as soon as I move this here, this guy now has a pointer count of 1. This guy has a pointer count of 1. Now I'm advertising that this guy will get automatically cleaned up. Why does it get automatically cleaned up? Because at the end of this method, node to return has a local scope. That variable disappears. Now I have this chunk of memory that's just floating out there. There's no way of getting to it. Garbage truck comes by and cleans it up. Make sense? All right. Yeah, and the thing is, I know I use kind of loose analogies, but I think they're far more accurate analogies than most books use. It is a garbage truck, and it comes and picks up dirty memory. Right?
There's no owner.
Yeah, we don't need to overcomplicate things. We've already talked about design patterns and all this stuff. We already have enough funny names floating around that mean easy stuff, right? We want to be good programmers from a skill set perspective, not, masters of the people who try to sound like they're smarter than other people. Make sense? We'll do this with our actions. All right, so that guy will get garbage collected. So last thing we did is we returned that payload. So that guy has now been removed from the list, but we've preserved his value if we would like to. If we'd like to use it, we can. Okay? So let's go back out here to our driver. Here's our current list. So let's go ahead and do remove front. So I'm going to say ll.remove front. We're going to get an error. Okay? Because remove front, as we've written it, throws an exception. So that means I have to deal with that exception. All right? So I have two choices. I can either put this guy inside of a try catch, or I can just pass the buck. So I can just say, okay, well, something in here could throw an exception, so if it does, I'll just toss it to the next guy. So it'll throw it up to the virtual machine. The virtual machine will just print out the error message. As opposed to this, where we would have said, try to do this. Catch an exception if something bad happens, and then handle it. Something like that. All right? So this would be the more appropriate way of doing it if we intended to do something about the error. All right? In our case right now, we're not going to do anything about the error because we're learning more about the data structures and how things connect to each other rather than writing an application that needs to handle errors and stuff like that. All right, so for our example, I would say that's appropriate. But in general, I would say this is bad programming practice to constantly pass the buck. Okay? But we'll go ahead and remove front. Right now, I'm not doing anything with it, but I could. I could say int val is equal to whatever remove front did. We'll go ahead and display that. And then I can say system .out.println val. Okay, so we added a 5 to the front, we added a 7 to the front of that, we added a 3 to the end of that, then we removed from the front. That should take away the 7. We'll go ahead and display it, so this should show us 5, 3, end, and then we'll print out whatever val was, which should be the 7. So there's the 5, 3, end, and there's our 7. Make sense? All right, so that's remove front. All right, now remove end. Removes and returns the payload of the last element in the list. All right, right off the bat, we can help ourselves a little bit. So let's go into LinkedList, and we'll do remove end right after add end. Public int remove end if head is equal to null. Oh, actually, that's gonna throw an exception anyways. Oh no, we're okay. We're okay right now. Yep. So we'll do this. So that'll throw the exception. So that just allows us to not have to handle the exception in 2 places. Okay. Else, if head is equal to something, that means there is an end to the list. Could be the one list though. And we'll talk about that a little bit more when we kind of get to that point. But at the very least, if we're in this else, we know that we're not dealing with the empty list. All right. We might be removing the one element that's in the list. Okay. But it's not the empty list. There is an element to remove. So let's look at our picture here. So if I say remove end, here we'll go ahead and just get rid of this guy. That means I ultimately want to remove this value. All right. So in order to remove this value, what do I have to do? I have to get to that value. I have to get to the node whose next node is a node that has no next node. Make sense? This guy has a next node, but his next node does not. So if I can get to this guy, I can then disconnect him. Make sense? So I need to get to the second to last node. So I'm going to start a variable off called Cur Node. We'll start this guy off pointing to the same place as head. All right, and then as long as Cur Node's next node does not have a next node, but we also need to make sure that Cur Node has a next node. All right, and what I mean by that is, let me just quickly show this. I almost treat this as a special case. What if I have the one list? If I have the one list here, Cur Node and head both point to the same thing. If I ask right now, does Cur Node's next node have a next node?
No.
Cur Node's next node is null. So if I ask a null value, do you have a next node, it's going to be very upset with me. Okay, Java's going to scream bloody murder and stuff like that. Okay? So we need to make sure that Cur Node first has a next node before we can ask, does Cur Node's next node have a next node? Make sense? All right, so we're going to ask the question. So we're going to go ahead and we're going to say node Cur Node is equal to head. Then we're going to say while. So we know that head points to something real if we're in here, right? Okay. Then we're going to say while Cur Node dot get next node is not equal to null, and so as long as Cur Node has a next node and Cur Node dot get next node dot get next node is not equal to null, Okay? If both of those things are true, okay? If Cur Node has an X node and his next node has an X node, then what are we going to do? We're going to set Cur Node equal to Cur Node dot get next node. All right. Once we're out of this while loop, Cur Node will be equal to the position right before the last element of the list, except if it was a one list. So I need to make sure that Cur Node at this point is not equal to head. Because if we had our picture that looked like this, let me delete this again. We're not dealing with the empty list. Cur Node is not, Cur Node's next node is equal to null, so we'll fail right away. Correct? We'll fail this right away. So at this point in time, when we're out of that while loop, Cur Node and head both point to the same place. I ultimately want to return this guy. That's the guy I'm removing. But in this particular case, if Cur Node is still equal to head, it's the one list. So we want to actually go ahead and set head to null. That's a special case for us. Correct? Otherwise, what are we going to do? Otherwise, Cur Node is not pointing to the same place as head, so we're not going to be messing with head at all. Instead, Cur Node might be pointing to this. And what do we want to do here? Well, we want to go ahead and preserve this guy so we can return his payload. Then we want to disconnect Cur Node from that guy and then return the payload. Okay? So we'll ask the question here. We're going to say if Cur Node is equal to head. If they both point to the same place, then what are we going to do? We're going to say head is equal to null. I'm sorry, head is equal to null. And then return Cur Node dot get payload. Right? So that's if Cur Node and head both point to the same place. That means we have the one list. Go ahead and just set head equal to null. We're out of stuff, right? Okay, we're back to the empty list. And then let's just return the payload associated with whatever Cur Node points to. Cur Node will die off at the end of this method, so garbage collection will come and pick up that node. All right. Otherwise, we're sitting right here. So otherwise, Cur Node currently points to the node whose next node is the node we want to return. So we're going to say node to return is equal to Cur Node dot get next node. Then I'll say Cur Node dot set next node to null. That'll disconnect it. So what I just did here is I said node to return is going to point to Cur Node's next node. Then we're going to say Cur Node set your next node to null. Okay. Then I can go ahead and return node to return dot get payload. That make sense? Oh, it still wants me to, yeah, because I have to deal with it here. Just do that. All right, so rather than build the exception twice, we just built the exception once and we just throw it here. A little bit of a hacky thing, but whatever. Okay, so remove end. If it's the empty list, we'll just call remove front, which we know already handles the exception thing. And then whatever exception he comes up with, we'll just throw. So that prevented us from having to rewrite this exception thing here. So didn't really save us tons, but just a little bit. That way we can stay consistent with the message, with the error message. All right. Otherwise, We'll go ahead and start at the beginning of the list. We're going to traverse our list as long as the current dude has a next node and his next node has a next node. We'll keep kicking him down the line. As soon as we break out of that, we need to make sure we're not currently looking at the front of the list, because if we are, then we need to treat that as a special case. Go ahead and reset our list to empty, and then go ahead and grab and return the payload, the guy we're currently looking at, because he's the only guy to return. Otherwise, let's grab the next guy, who's the actual guy we want to return, update Cur Node's next node to null, and then return the payload. Okay, so that's remove end. So let's come back in here. So right now we're doing, here, let's just do a remove end there. So this should be a 753. We're going to remove the 3, display the list. So should we just have 75, and then we'll display the 3. So there's 75, and then there's the 3. Okay. Now let's keep whittling it down to make sure it works on our. So I'm actually not even going to store it in val here. So we'll remove end, remove end, remove end. So here, if I remove end a second time, now we'll be looking at just 7 as our new list. Ooh, hold on. Bugs. All right, so 7.5 is our current list. If I remove end again, I should just be stuck with the 5, but that's not the case. So we have handled our walking incorrectly. So let's see, we have a list that looks like this. Whatever's wrong with the code, I did on purpose. Row. All right, so we start off with Cur Node is equal to head. And then we say Cur Node's next node. Okay, yeah, this is where the problem is. So first we ask, does Cur Node have a next node? Yes, it does. Does Cur Node's next node have a next node? It doesn't. So we actually leave it right here. So right now our logic says that both of these guys, we say if head and Cur Node both point to the same place, then we're emptying the list out. But that's not the case in this particular situation. We need to ask an additional question. Does Cur Node have an X node? If it's equal to head and it has an X node, we still do the other thing, which is going to be node to return is equal to this guy. Then we can disconnect this guy, so on and so forth.
So there are
So-
two possibilities with Cur Node will equal to head. One is this now, and
Yep.
the one there's only one.
Correct. So we actually want to write this like this. So we're going to say, I'm lost. Where are we? Okay. If Cur Node is equal to head and Cur Node dot get next node is equal to null. So if Cur Node is equal to head and Cur Node does not have a next node, then we'll go ahead and empty the list. Otherwise, do our normal protocol. So there's our 7 and end.
Actually, you can delete the kernel equals to head.
Delete who?
The kernel next node is equal to.
You're right, we could. But I mean, I guess I prefer to be
Yeah.
verbose there.
Yeah.
Um,
But I mean, logic.
yeah, this guy assumes that this guy would be true. So let's see. So let's go here. So that removes end there, and let's do another remove end, which should then give us the empty list. There's our empty list. And then if we do another remove end, we should get our exception. Empty list exception, can't remove from empty list. All right, that's the one we wrote. Did I? Oh, that's what you were joking about, broken English? Oh. I was telling you guys what not to do. I told you I did that on purpose.
You will reduce our credit if I didn't make this mistake.
I have an excuse.
Yeah, you only excuse.
13-hour a day all programming. I've been staring at this stuff for 13 hours. Not even the same language. Yeah, today's been Swift, Python, Ruby, Java. I think that's it today.
That's a lot.
Yeah, so it's a good day. I'll probably sleep very well tonight. And I'm still coming off my my trip from Denver, where I was at a really high elevation. It's like 7,000 feet there. Well, I'm not used to that. You don't know how that affects you. I was exhausted. Just from lack of oxygen or something. You don't know it's from that. You don't just, I usually go to bed at 11:30 or 12, and I'll lay in bed for an hour and watch TV. Or 9:30 at night, I am gone. Okay? I could barely walk straight. So, so I'm still recovering from that. I just got back Monday night.
Is that the day you drink a lot?
Huh? Oh yeah, it is the day I drank a lot. Yeah, I found a brand new place in the airport. It's called Vino Voyo. It's like a wine bar. Well, it's like in all of them. Milwaukee has one, and then they had one in Denver. Apparently, they have it at a zillion different airports. And when you join there, I'm already like an ambassador. I spent like $200 there. I've only been to 2 of them. I had a big layover. Yeah, I mean, I'm a big wine drinker. I love wine. Just sit there and just drink a couple bottles of wine before you get on the plane.
White or red?
Oh, I'm a big red fan. But when you start, when I started, I was into like White Zinfandel or something like that. But now I like the really thick stuff. I like really old Cabernets. Love that. But not a beer drinker though. I don't really like beer. I mean, I'll drink it, because I'm from Milwaukee, but because when I moved here, that was the 2 things. They had to say, okay, well, you drink beer, right? I said, yeah. Well, not really, but I will. And then I also had to sign saying I was a Packers fan.
You had to declare.
Otherwise, they wouldn't give me a driver's license.
You said you're originally from Kentucky, right?
Well, I was born in Kentucky. I grew up in Illinois. So, I mean, I moved to Rantoul, Illinois, near Champaign, Illinois, when I was 1. So I lived near the University of Illinois for most of my life. And then, and that's probably where I kind of got into the computer stuff, because I grew up during the time period where like the internet was being born. So, the internet was kind of invented in Champaign, 10 minutes from my house. And I worked at a computer lab there at NCSA, National Center for Supercomputing Applications, where the Mosaic web browser was created. I was this little kid working in this lab, and I was jealous of those guys, so I would learn from them. So I started programming when I was 9, but my mentors were the people who wrote, Mosaic and invented the internet. So that's probably kind of why I got into programming so young, as other kids were out playing soccer or whatever. And I wasn't doing that. I was I was a 9-year-old hanging out at the university. There's all sorts of weird things that go on with that in terms of mental problems. But I guess it turned out okay. All right. So anyways, that's remove front, remove end. We have our exception handling stuff. Okay. So what would logically come next? Come back to this guy. Add at index. This adds a new node at the specified index in the list. Right? So if I come back here, and ooh, I didn't expect it to work that way. Redo. There we go. I expected if I came onto this screen that it would undo the things that I'd done here. Life is over. All right, so here we'll just add one more little node in here. All right, so we have these guys. So let's say we want to create a brand new node. We'll go ahead and just grab this guy. And we're going to add a 4. And let's say we want to add 4 at index 1. So this is bucket 0, bucket 1, bucket 2. So that means in the end, we want 4 to be the new bucket 1. So we want our list to ultimately look like this. Make sense? What we want to accomplish? All right. So in order to pull that off, we need to move ourselves into the position. So notice this guy is going to be the guy who points to this guy. So we need to move to the position immediately before the place that we want to get into. Okay? So let's do this for the generic case first, where we assume that there's stuff before and after and that kind of stuff, and then we'll handle the special cases. Okay? So we're going to say added index. So let's see, add front, remove front, add end, remove end, and let's do added index here. Okay. So there's added index. We're going to take in a value and we're going to take in the index. Now right off the bat we can say if head is equal to null, we can say this dot add front value. Well, actually you're right. You know, really this is going to be kind of a implementation decision. If they say I want to add something to bucket 6 of the empty list, do we still add it to the list or do we throw an exception? Yeah.
I think it depends on how we make it.
Yeah. For right now, I think we need to write it this way because we haven't implemented our list yet to keep track of how many things are in it. We can't ask the question right now, is index, well, we can't conveniently ask the question right now, is index out of bounds? Does that make sense? Because I don't know how many elements are in my list. We could keep track of that, right? I could say that I'm going to expand my definition of linked list to have a private int count. And we'll say this dot count is equal to 0 by default. Every time we add something, we're going to say this dot count plus plus. Every time we remove something, this dot count minus minus. Add front already handles the count, so we need to make sure we don't do the count twice there. So this is add end. So we just added something there. Remove end, so remove front already handles the minus minus, so remove end here. Let's see, we need to do, I think we can do this right here. Yeah, if we're in here, we'll definitely be subtracting 1. So if we're in this else, we are definitely removing something from our list. How we remove it is up in the air, but we're removing it. Okay. So now that we have a count, you know, we can prove that real quick. So let's when we say display, let's just do system.out.println this dot count, and then we'll do the whole display stuff. So given that just get rid of some of these removes. So this should show 3. Count is 3. Here's that stuff. Remove end. Count should now be 2. Okay, so let's just do remove front to make sure that guy. Okay, so now we actually have a count. So we can actually ask the question, are you trying to add it to an illegal position? Okay. So added index, rather than saying head equal to null, we'll say if index is less than 0 or index is, let's see, if there's a count of 5, the legal buckets would be 4. So adding something, if it's greater than, if we say added index 5, that would mean add end. So really it needs to, if index is greater than count plus 1 is the error, right? If the count is 5, no. If the count is 5 and we say we want to add at bucket 5, that means if count is greater than, if index is greater than count, it's illegal. If it's less than 0 or greater than count, it's illegal. Otherwise, we can add it. Okay, so if index is less than 0 or index is greater than this dot count, if either of those are true, we're going to throw new exception add at index out of bounds. Here we'll give them a nice little error message. An index. All right, and then this guy will throws an exception. All right, so if the index they asked us to add it to is out of bounds, we'll say out of bounds, right? We'll give an error. Else, if index is equal to 0, this dot add front value. Else, if index is equal to this dot count, this dot add end value. Else, we need to do the adding here. Okay, so it's either an illegal position they asked us to put it into, or it's the first position, so we'll just rely on our add front, or it's the last position, so we'll rely on our add end, or it's somewhere in the middle. Okay, but somewhere in the middle, that's where we need to do our tricky stuff. So what does somewhere in the middle say? All right, so if this is the guy we're adding and we said bucket 1, let's say, we need to traverse our list until we get to the guy immediately before bucket 1. Okay? Now, right off the bat here, let's see, is this necessarily tricky? Because since I've already ruled out all the extremities, I know I'm not adding to the front end or illegal position. Therefore, I just need to go to index minus 1. I know index minus 1 would never be in a legal position. Okay? Because if I was still here, index is at least a 1. And I need to go to 0. So I need to get a pointer that goes through my list up to but not including the position I want to get to. Okay, so we'll do something like this. So let's say move to the pos right before index. So we'll say node cur node is equal to head. We'll start there off the beginning. We'll say for int I is equal to 0. I is less than index minus 1, I plus plus. Okay, so let's see if I'm going to add it at bucket 1. Okay, actually, I don't need to say minus 1. I think it's just less than index. Yeah. So start I off at 0. Keep going as long as I is less than index. I plus plus. And what am I going to do each time? I'm going to say cur node dot set. No, I'm going to say cur node is equal to cur node dot get next node. So that was kick it down the line a little bit, right? All right. And then once I've kicked it down the line a little bit, then I'm going to go ahead and we're going to do our logic, which is right here. So logic's going to say, so I'll be pointing right here. So I'm going to say this guy dot set next node to this guy, but not until after I've taken my new node and connect him here. So I need to go ahead and create my new node, set him equal to cur node's next node. So we'll say node n is equal to new node value. Then we'll say n dot set next node to cur node dot get next node. And then we'll say cur node dot set next node to n. All right, and that should add it. Okay. Because we're running short on time, I need to show you one additional thing here. So I'm going to give you this code as the starting point. But I'm going to show you, so give me 2 or 3 minutes here if you'll let me, because we're going to use GitHub in here. Okay, so it's an online tool for distributing code and things like that. So I'm going to put this up on GitHub so I can give it to you. All right, so then by me showing you how to do that, when you do your homework, I want you to submit your homework to GitHub and then put a link. Give me a link when you submit it, rather than attaching the code. Okay? So you'll see what I mean here in a second. All right, so ask any questions after you see it. So give me like 2 or 3 minutes if you'll let me do this. Otherwise, if you don't want me to do it, I won't give you the code. All right, so you go to the website called GitHub, github.com. There's a tool called Git, and Git is creates a local repository on your computer. Okay, and so you can go through set up Git, all this stuff. It gives you kind of a guide, a tutorial for doing this. I'm going to show it to you on the Mac. If you download Git on a PC, you'll use the exact same commands that I'm doing here on the Mac. The Mac comes with Git already installed. So what Git is, it creates a local repository of your code. So it keeps track of all the backups you've ever made and all the changes you've made, things like that. What GitHub is a remote website that you can store Git repositories in. So it's a good way of sharing code. So for instance, I'm going to push this code up to GitHub so I can share it with you. When you do your homework, you're going to put your homework up on GitHub so you can share it with me. Okay? Make sense?
How can you know that homework was from me or from?
Because it's going to be linked to your GitHub account. Yeah, so here, you'll create an account on here. I'm already logged into my account. So once you log into your account, what I'll do here is, so I'm going to create a new repository. This is on GitHub. And I'm going to name this repository CSC537 linked list. Okay, that's going to be the name of this repository. And it's going to be public, otherwise you have to pay for it. So I'm going to do create repository. Okay, it's going to actually give me the instructions I have to type in. okay, to make this work. So I'm going to go through this. There are some GitHub plugins for Eclipse. I don't recommend them. So we're going to do this the kind of the long-handed way, but it's not too many commands. All right, so after you get Git installed on your computer, which you can follow the directions that, it takes 5 minutes. You just download it. It's going to give you a terminal, okay? A terminal that looks kind of like this. All right, so if you're on a Windows machine, when you double click on Git, it'll open up something that looks like this. All right, and then what I'm going to do here is I'm going to change into the directory. So let me just make this quick here real quick because I actually keep my code inside of Dropbox. Let's go in here, and here, and here, and here. All right, so there it is actually. All right, so I went ahead and I just moved into that directory. This is my Eclipse project. Okay, so this is my LinkedList project. I have 2 folders, bin and source. You actually want to go into the source folder right here. Those are our 3 files. Driver.java, LinkedList.java, and Node.java. All right, once you're sitting in that directory, that is, when you type ls, which is a Unix directory command, if you were on a DOS machine, you type in dir. But when you are on a Windows machine and you download Git, it'll give you a Unix terminal. So it'll always be ls. So you should be able to type in ls and see that.
Is that in PowerShell?
Okay. And then what I'll do here is we're going to go ahead and create a Git repository. So all the commands are listed right here. Git init. I never do the README thing, so you can skip that. But let me just show it to you here. So I'll go ahead and I'll grab this command. So this is git init. That will create a initial Git repository in this, let's see. That's weird. It must be because I just updated the, you won't have to do this each time. I think there was a new version of Xcode, and Git for the Mac comes with Xcode, and there was just a new version, so they're making me agree to something. So that isn't part of the normal thing. So in any case, what just happened is it just created a directory in here called .git, okay, which is my local repository. Any directory has a period in front of it is hidden by default. All right, so now I have a local repository. The next thing it wants me to do is I'm going to actually go ahead and add the command. So I'm going to do git add star.java. So this adds all of my Java files that are in the current directory to my repository for files I want to track. Okay, so I'll do git add star.java. Now if I do a git status, it shows me that these are, oh, I haven't actually done my initial. One second. Okay, see, that's just, yeah, I think I basically broke it by having to agree to that thing. So you shouldn't have to do that when you do yours. So now I do a git status. Shows me I have 3 new files that I'm adding to this thing. So sudo git commit -m. Let's just call this initial commit like that. So it created these things. These are the same files here. So this is the git commit -m. I've had to do that sudo thing, which allows me to run it as super user because of this agreement thing. It shouldn't happen to you. All right. Now, this is the important part for GitHub. So everything I just did has committed everything locally to my local Git repository. Okay? Now I need to take that local Git repository that lives on my hard drive and push it to GitHub. All right, so the very first time, you need to go ahead and let your local repository know about your remote repository. So again, I have to do this sudo thing. So I'll do git remote add origin. So basically just copy the line that they give you right here. this line right here. And now I've added, it creates a local variable that knows about your remote repository. You only have to do that line one time. Okay? Then this last one, this will push it. Okay, so now it's going up to the cloud. The very first time you do this on your machine, you'll have to put in your GitHub username and password in order for it to work. But then ultimately what will happen is now I have these files up there. So here's that repository, so I can now put this link on your assignment, and you'll have this as your starting point. So you can just go to this website. Once you go here, you'll have a button to clone it, so you can just download a zip file that has these 3 things. Okay? But for your homework, when you submit it, go in here, create a repository, upload it to it, watch this video, see what I just did, or follow the tutorial on the GitHub website. Really good tool, something you'll definitely use in industry. Okay? You'll use it all the time in industry. All right. Questions, comments, concerns, bribes? All right, I'll put this link up with the homework assignment right now so I don't forget. I'll also put up the link to the video lectures. Same time, same station next week. If you have any questions about the homework, feel free to ask. I will be sending everybody an invite to something called Slack, which we have here on campus. Some of you might already be on it, but for our computer science department, we have a whole chat group thing set up. I'll create a course for this one where you guys can ask questions in there. It'll be a quick way for me to respond to you and also for other folks to see my response. Okay, and also for you guys to ask questions of each other. All right, so one thing I guess I'll point out that I know you run into some of the other classes, obviously, some of your cultures encourage collaboration, right? Okay, I don't mind that. I encourage you to work together on this stuff, but understand that your ultimate goal is to learn the stuff, okay? What I don't want you to do is turn in somebody else's work. If you're going to get together in a group of 2 or 3 people, I want you to help each other, but ultimately each turn in your own solution. Or if in the end you feel that your solution is too close to somebody else's, in your self-evaluation, and go in there and read the instructions, I want you to kind of post something with everything. Just say, I worked with so-and-so, our solutions might seem similar, but we worked independently or something like that. You know, just don't try to pull the wool over my eyes, okay? I don't want you to cheat, but I do want you to learn, and sometimes the best learning environment is a collaborative environment. Make sense? All right. I will see everybody next week.